area. That's why the first edition is taking place there. And they have a lot of experience in organizing these kind of events, primarily from organizing the International Linguistics Olympiad and the European Junior Olympiad in Informatics. And these are the people that make up the scientific committee. A lot of people from a lot of countries, most of them with an academic background, some of them working in industry. So hopefully some of the things I'll cover today, you're already familiar with from looking at the website. If you haven't familiarized yourself with the IOAI website, do so. There's a lot of important and useful content there. Today I will cover most of it, as well as some additional new content. And based on your questions at the end of this session, we will update the website with additional information where necessary. So the format of the Olympiad is the following. We are covering 3 topics, the 3 main topics under the umbrella of AI: machine learning, natural language processing, and computer vision. And the Olympiad takes place in 2 rounds, a scientific round and a practical round. The scientific round is the more challenging one of the 2. It forms the main component of the final score, and actually, most likely it will form the main ranking of the Olympiad. It includes coding, training models, solving tasks with machine learning on a level that is close to what is happening in research, and that is close to what is happening in the real world in terms of problems. The practical round is more fun. It's a smaller component of the final score, or most likely a separate, smaller ranking on the side of the main one. And it will involve solving a task through interaction with an off-the-shelf model, AI agent, like ChatGPT, for example, where students might be asked to do some kind of prompt engineering, for example. Today, I will mostly talk about the scientific round, as this is the more, solid component of the Olympiad. I will just briefly cover the practical round, and later on in the coming weeks and months, we might have further details about the practical round, but generally that is a round that, you also as contestants and team leaders should be less worried about. It will require less preparation, so to say. So the scientific round will have 2 stages, an at-home stage and an on-site stage. In the at-home stage, teams will get 3 shared task style problems, and the date when these will be released is June 30th. The teams will work on a solution to all 3 problems and submit their work on August 4th, which is exactly 1 week before the core day of the Olympiad. More dates will come later on, at which point we, the scientific committee, we will evaluate the solutions and prepare for the on-site stage. In the on-site stage, the teams will get new subtasks expanding on the same 3 problems. And when we say subtasks that expand on the problems, what we mean is that we might either ask the students to build on top of the system that they already developed at home, or we might ask them to develop a solution for a similar problem to what they saw at home, but with new data, or with a new angle to the same problem. But generally, the idea of these 2 stages, especially because we are aware that high school students don't have a lot of background in AI, is for the at-home stage to be educational and to be sufficient to prepare the students for the on-site stage, where they will already be familiar with the general framework of the problem and will just have to adapt the knowledge that they obtained at home to a new subtask within that same framework. So on-site, the students will have 8 to 9 hours to develop solutions to the 3 problems. And there will be the possibility to let models train overnight for up to 8 hours. More detail on that will be provided later on, but technically the solutions should be ready by the end of those initial 8 to 9 hours of working, and any further training has to be set up in advance. The students will not get repeated access to their models and code and so on. more on that later. I don't want to go into too much detail now. The final score for the scientific round will be based in small part on the performance of the systems developed at home and in large part on the performance of the systems developed on site. As you can imagine, the reason for that is that when the students are at home, we don't really have a way to ensure that they're working on their own, independently. And like I said, the at-home stage is meant to be an educational stage anyway. This is where the team leaders should be very involved with guiding the students to the right materials, resources, coding frameworks, and so on to learn how to solve these kinds of problems. And then on site, we will actually test how well the students develop these abilities and skills. The practical round, again, just very briefly, to give you one example task, we might ask students within an hour time to find a way to communicate to another human being through the text box of ChatGPT without the model being able to understand the content of the message. And to give you an example of one possible solution, if you type the message, say hi, in in ChatGPT's text box in this fashion, the model is not able to decode it. When it comes to the scientific round, as we say here, performance is based on the scores are based on the actual performance of the systems. So we will be using objective automatic evaluation metrics to score the team's solutions. We are completely, leaving out the sort of human judgment component, because unlike disciplines like mathematics, informatics, physics, where there is usually one solution that can objectively be determined to be correct for a given problem, in AI that is not the case. AI is largely an empirical discipline. There's many different ways in which a problem can be solved, so to say, correctly, but in the end, some of these are going to result in higher performance on certain metrics than others. And of course, there are certain ways to try and solve a problem that are incorrect, but usually those faults would be reflected in the performance of the system anyway. So we deem the automatic evaluation metrics as the best and most objective way to rank the solutions of different teams. In contrast, for the practical round, we might resort to more human-based evaluation, either by the members of the jury alone, or actually by a wider audience. This is yet to be determined. Going on to the technical specifications for the Olympiad, teams should bring a minimum of 1 and a maximum of 2 laptops on which they will be developing their solutions. There are no special requirements for the hardware capacity or anything of these laptops. They should just be able to connect to the internet. The reason for that is that all code development will happen in an online web environment, specifically Google Colab. As the organizers will provide this environment, as well as sufficient GPU compute credits for the, adjusted to the requirements of the different problems we're giving. And we are asking and formally requiring that teams do not use any additional GPU compute on top of what we are providing. This is to ensure that all teams have an equal basis. The problems will be distributed as links to a Google Colab notebook. They will be sent out to team leaders, who will then have to distribute them onto the contestants. Upon completion of the at-home and on-site tasks, teams will be asked to submit their code, their models, and a file with model predictions on a test set provided by the organizers shortly before the deadline. This is for the at-home assignment. For the on-site task, we might set up an online platform for evaluation. which will also have an associated leaderboard, so students can continuously submit their solutions throughout the day, see where they rank, and hopefully get motivated to do better and better. The final models developed should take no longer than 8 hours to train and no longer than 1 hour to perform inference on the provided test set. And we might impose even stricter constraints on a problem-to-problem basis, as for some problems, 8 hours would be quite an overkill for training. We might be looking at much lower times or longer ones in some cases. But this is the general guideline. In terms of necessary background, so hopefully the students that have signed up for this Olympiad, or at least some members of the teams, already have some of the necessary relevant background. We're talking about a practical understanding of basic linear algebra, vectors, matrices, dot products, and so on. Intuitive, at least, if not practical, understanding of probability theory and calculus, as these two fields underlie much of machine learning and deep learning. Knowledge of the Python programming language or another programming language, as it can be a pretty fast transition, but the more knowledge and skill at least some team members already have in Python, the faster they will be able to dive into solving the problems. And the ability to search for coding advice online and to debug code. It's not enough to just know the basics of Python if you don't know how to extend your knowledge, basically. In addition to that, team leaders should further enhance the students' background on the fundamentals of machine learning, natural language processing, and computer vision. These three, again, are disciplines that students would not necessarily be familiar with. The goal of this Olympiad is to motivate and facilitate high school students to enrich their knowledge on these topics. And finally, to test how well they did that. A little bit more on the role of the team leaders. In preparation for the Olympiad, team leaders should educate their teams on the aforementioned topics using the lectures provided by the IOAI today, for example, and next Monday, as well as online resources such as the ones that we've suggested on the website, and of course their own knowledge and expertise as well. During the at-home stage of the scientific round, team leaders can provide subtle guidance, but it is quite important that they allow students to exercise their own creativity and self-learning, as this will put them in a much better position to perform well in the on-site part of the Olympiad. And team leaders are strongly discouraged from writing any code, performing debugging, executing experiments, or carrying out error analysis unless absolutely necessary. Let your teams be stuck for a few days, for a week, guide them to how you would go about resolving the problem, but only in the most extreme of cases resort to actually getting engaged with their code and models and so on. During the on-site stage, teams work completely independently with no help from the team leaders. Now, they cannot get help from the team leaders, but of course they can get a lot of help on the internet from websites like Stack Overflow and also from coding assistants. We will not attempt to forbid this. We believe that this is part of the experience of anyone working in AI to be able to go to the internet and find an answer to a question. We've designed the problems such that they cannot be trivially solved by just asking ChatGPT to solve them for you. So we allow contestants to use any code and information that they can find on the internet, both during the at-home stage and the on-site stage. Coding assistants are allowed, again, during both stages, but their use during the on-site stage is limited to free-tier, non-subscription-based services, which means that it's okay to go to ChatGPT and ask it for a recursive function to do X, but using GPT-4, Copilot, or other paid services is not allowed. Lastly, there will be no outgoing communication during the on-site stage, which is to say, Contestants can go to Stack Overflow and search among the questions already asked. If they can find an answer to what they're searching for, great, but they're not allowed to, for example, post a new question. And obviously they're not allowed to, I don't know, shoot a WhatsApp message to their team leader. This is the general timeline for the time between now and August 15th. So registration closed on May 30th. We are in the online training part 1 now, June 10th. Next Monday, we will have online training part 2. On June 30th, the scientific round at-home problems will be released. And then we expect all solutions to be submitted by August 4th. On the 9th of August, the teams should be arriving to Bulgaria. On August 15th, they will be departing. And in between those 2 dates, the schedule looks like this. We have arrival to Burgas on the 9th, opening ceremony and some lectures on the 10th of August. 11th of August will be the scientific round. On the 12th of August, there will be an excursion. On the 13th, a practical round. On the 14th, we will host a closing ceremony, again with a mini conference. And on the 15th, teams will be departing to their home country. Last point, we will set up a Slack space for communication. All team leaders will be invited to this space, and they can use it to voice questions, concerns, and requests. But beware that we may choose to abstain from answering some questions, and others we might choose to answer publicly for the benefit of all teams. And contestants will not be admitted to this Slack space. So team leaders will be managing the communication with the IOAI organizers. That is all. Thank you. And I turn to Rossi and Laura for any questions from the YouTube chat.
Okay, so these are the questions so far. Is it mandatory to use PyTorch as the deep learning framework?
The way the problems are set constrains the students in terms of what framework they will be using, because a lot of, well, at least a couple of the problems rely on pre-trained models or pre-training frameworks. We're providing some starting code or a baseline and asking the students to build off of that. So while it could be possible to, completely shift everything to another framework, and we will not disallow that, it might be highly disadvantageous for the students, because much of the code already will be set up in a specific framework. I believe in both cases that is PyTorch.
Okay, thank you. Regarding this video, yes, it can be watched permanently. What about the slides, Jova? Will they be available in some way?
Yes, so yeah, actually about the Slack channel, in the coming days, team leaders will receive an email with an invitation to the Slack channel, and alongside that, they will also get a link to the slides and any associated materials from today's presentation.
Okay, thank you. There is a question about the free tier services that the participants are allowed to use, whether they include services that are limited access without subscription.
I don't know what that would be. Limited access without. So the idea of this constraint is to make sure that all teams are on equal footing. So if the service you have in mind can be accessed by anyone freely, without subscription and any special sort of membership, then yes, it can be used. Although I would prefer if once we have the Slack space, shoot us a message with what exactly you have in mind, and we will just double check to confirm.
Okay. Are there any restrictions on using external machines like local GCP or AWS in this in the at home
Yes.
section?
Yes. So we request the teams stick to the resources we have provided, partly because we have chosen the amount of credits available to the teams according to what we believe is a reasonable amount of compute for solving these problems. And this is part of the learning experience to figure out how to solve a problem within the compute budget that is given. We don't really have a way of controlling that teams abide by that. Another reason why the score for that at-home component is the weight of the score is fairly low. But yeah, my advice is stick to what we have provided, because if teams develop skills and strategies for solving problems with a large amount of GPU compute, and then on site they find themselves much more constrained, they might struggle to adapt.
Okay. There is a question about students on the waiting list. So probably the teams are not formed. Are they allowed to do coding in the at-home section?
Rosie, do you know what this question is? Because I don't understand how the two things are connected. What does it mean? Are they allowed to do coding in the at-homes? Like if teams are formed later, they will just have a later start, but yeah.
So if teams are formed later, they will have to have a later start.
Yes.
Is that okay? Thank you. There is a question about the battles mentioned in the website regulations, whether they will still be hosted.
I believe no. No. I think there is still a little bit of uncertainty and flexibility around how we will set up the practical round. We might play around with the concept of battles there, but they will not be part of the main scientific component. The original idea for those battles was based around how do we set up an objective evaluation. In the end, we settled on just pure automatic metrics. So that's why the battles have become obsolete now. We will update the website about that.
Yes, and I think it is similar for the questions about the difference of the schedule on the slides and on the regulations page. So the regulations page will be updated, and please follow what was provided right now by the team, by the jury jury chef. Okay. There is one question about, like, for example, ChatGPT using GPT-4 for a limited number of tokens and then goes back to 3.5. I'm not sure what the real question is, but as long as you are using it freely and not paying for it, it should be fine.
Yeah, so if this is a limitation of GPT-4, it's irrelevant based on what we said about the use of GPT-4 altogether being, discouraged or completely forbidden during the on-site stage, because GPT-4 at the moment is a paid service.
Okay, let me see. Will we be judged on our team-based work on the problems or individually?
As there is no way at the moment to disentangle individual contribution to the team solution, we are, the main ranking will be based on the team's performance, and all members of the team will be awarded as one unit. We are looking into ways to elect to build up on that with some sort of individual ranking, but for the time being, that has not been sorted out. So the only thing we promise is a team ranking.
Okay, there are no more questions so far.
Okay, we can give another 30 seconds if anyone is in the middle of typing something. And then we will move on to the first machine learning lecture by Dr. Maxime Panov.
Okay. One question is one contestant or one participant is asking about the answers to the sample problems published on the website, whether these will be made available.
Yes, I guess we can do that. I will need to confer with the colleagues from the scientific committee, but yeah, I can at least say that I see no problem with that. We can try to work it out.
Okay. Another question about the overnight training.
If I can, Rosy, just yes. to say one thing on that, actually. Again, because AI is not a precise discipline in the sense of, there's no one single good solution. I think that's why we originally didn't post any solutions, because there's many ways in which a system can be improved, and these can go in completely different directions. And we can post some sample solutions, but those will not be exhaustive and should not be seen as a reference solution, just as a one way a team could have gone about. We're not claiming that this is the best way that this could have been done. And similarly, this question came via email a few weeks ago on whether the after the Olympiad, whether we will discuss the correct solutions to the problems. We will discuss the best team solutions, but again, there is no one single solution. So with reference to the sample problems on the website, we might just post some sort of, this is one way someone could have gone about solving this, not even necessarily spelling out all the code, but these should not be taken as a gold standard. That's all.
Okay. There is a question about the overnight train period, whether participants are allowed to debug or modify the code during that time.
No. So this is the detail I said. Yeah, we can now dive into it. So the setup there will be, first, I think it will be in the best interest of teams to develop their solutions in the course of the day, precisely because of the potential problems that can arise with overnight training. For the overnight training, the only form which we will allow for it is for the code to be set up such that models are being trained, checkpoints are being saved, checkpoints are being pushed somewhere to an online cloud, and evaluation is set up to run automatically once the model is done training. All of this code has to be prepared and set to run before the official end time of the competition day. And ideally, there should be some safeguards in place, like a solution can already be submitted at the end of the competition day, and then this can be run in the background as, in case a better checkpoint or a better model gets successfully trained overnight, that can be come in as a resubmission.
Okay. Then there is a question about the final list of the teams, when the teams must be finalized for countries and confirmed with the IOAI team.
Well, all I can say in this respect is we're releasing the problems on June 30th. So any teams that are formed after that, will be at a disadvantage of having a late start. I don't know if from your side, Rosie, Laura, if you have any considerations in mind in that respect.
So let's say if teams are not finalized, we give them the problems later?
Yes.
So that there is no disadvantage, like one team working with 4 people and another team working with 12 people waiting to be finalized.
Oh yeah, in that sense, yes. The problems should not be tackled by more than 4 people.
Okay, I just answered the people who are asking questions that are not related to training. Please ask them additionally at our email, and we are not going to answer questions about coming on whatever day or schedule, the overall schedule, and so on.
Yeah, so any questions that might come up after today's session or next Monday's session regarding the scientific component of the Olympiad, you can bring to Slack. You will have access to that in a few days. Any questions on the logistics, direct to the IOAI emails, contact secretaries, and so on directly.
There is a question about time and memory complexity. Would that be a factor of judgment?
It will not contribute to the final scoring, but there is a limit implicitly on that in terms of how much GPU compute we're providing and what is the mentioned constraints on maximum time that a model can train or run inference for. So we're not making them part of the ranking, but they are part of the constraints for a team to succeed.
Okay, no questions so far.
All right. In that case, I will give the floor to Maxime.
All right. Hello, everyone. Let me share. And we will shortly start. Question was my screen. That should be browser. Is it visible?
Yes.
That's all right. Okay. Let us slowly start. So first of all, let me introduce myself. My name is Maxim Panov. I'm as well as IOAI, I'm assistant professor at Mohammed bin Zayed University of Artificial Intelligence, which is in Abu Dhabi, in United Arab Emirates.
If I can interrupt you just for a second, the visualization of the slides is now different than what it was before when we were testing.
That's for purpose. That's for purpose.
Okay, perfect.
Yeah, we will come back to the presentation mode shortly.
Okay.
Yeah. So. So my presentation today will be to give very brief introduction to machine learning and to some important topics within the area, and I will be followed up by Ali, who will be talking on more advanced parts of ML. And my presentation will have a little bit unusual format today, so it will be not just like PowerPoint and PDF slides. My presentation is done in Jupyter Notebook, and this is a special environment inside the browser, which is nowadays used very widely for developing AI solutions, like as a working environment for that. So it usually looks as you see it on the screen. So you have a certain control features, and then you have so-called cells, which can have text. As here, you can have pictures, and also you can have code. So code in Python or in some other languages as well. So this is a very nice interactive environment. I'm sure that all the participants of the Olympiad will interact a lot with it. And however, I will be using it for presentation purposes today. So I will now go to presentation mode. Yeah, and hopefully now you see the full screen. And let us start with an actual content. So basically, I will be covering 4 main topics today. So I will start with some introduction on machine learning and the types of problems which are usually considered. Then we will be talking about one of the fundamental models, which is called linear regression. Then we will continue with model selection and cross-validation. And we will finish with a very brief starting discussion on classification. All right, so let's start. And well, first of all, machine learning is currently the main driving part of AI. So AI is a more broad concept than machine learning, but the vast majority existing methods, models, and approaches in AI, they are based on machine learning. Machine learning consists of several different areas in terms of algorithms, and in terms of problem statements. So the first one, and probably the most widely used and mostly applicable, is called supervised learning. And 2 main problem statements or problems to be solved within supervised learning are classification and regression. The other part of machine learning is so-called unsupervised learning. And the most notable examples of problems in this area are clustering and dimension reduction. There exist many more problems and tasks, like, for example, reinforcement learning, but we are not going to cover them, at least at this edition of the Olympiad, so I'm just mentioning this for information. So let us go into some details and on the problem statements and the peculiarities. So first of all, we start with supervised learning. So in supervised learning, you have two important objects which you work with. One of them is usually denoted as X, and that's some description of an object. That might be a set of numerical features. It might be an image, it might be text, it might be many things. I will give some examples later on. And the second object is output, usually denoted by Y, which is some characteristic of an object, so some function computed. And you assume that between Y and X, there exists a functional dependence. So Y is some function of X. And the most important object which you work with is so-called training data set. That's a data set of pairs of X and Y. You are usually given several such samples, sometimes many, and altogether they're called training data set or training sample. Given this information, in supervised learning, you are asked to construct a prediction model, usually denoted as f hat, which is some mathematical function which maps from X to Y. So for any input X, it should produce an output Y, and it should mimic the original dependency. All right. So 2 most important examples of supervised learning problems are classification and regression. What is classification? Classification is a supervised learning problem, whereas the outputs Y can belong to a fixed finite set of labels. So you have these possible values, C1 up to CK, and the finite number of them. The simple example of such a problem is spam filtering. That's something which all of you are encountering when you use any of your email clients. They all do spam filtering. And in this case, input X is a text of an email, and output Y is a binary variable which tells you whether an email is spam or not. So as a result, you want to construct a model which will predict you one of the classes. So say, as in my pictorial illustration, we have two classes, circles and crosses, and we want to separate one class from another, and I have this separating line between them to illustrate what will be the classifier. That's a definition of a classification problem. And regression problem is something similar, but in regression, well, again, X's are some description of an object we are working with, but Y's now becomes a continuous variable. So Y now is not just one of the fixed numbers, it can be any number on a real line, for example. And even Y can be multidimensional, it can be several real numbers. So very like real world example of a regression problem, you have an aircraft which has certain geometric parameters, like Y can encode some, X encodes some parameters of an aircraft. So like its geometry, the shape of wings, the shape of a main body and so on. And Y can be some output characteristics, like, for example, the lift force or drag force or mass of an aircraft, or whatever other aerodynamical or other characteristics of an aircraft that's possible. We will work on some examples of some further examples of regression problems further during my talk. Okay, so these were supervised learning problems. The feature of these problems is that you have input characteristics and output characteristics, which are functions of inputs. The other part of machine learning is devoted to so-called unsupervised learning. In this case, you have no any outputs. You have only inputs, which are descriptions of an object, but you don't have any guiding signal like any output. So, and based on this input information, your goal is usually to learn some internal structure of the data. So to find some peculiarities of the data you have. And two main unsupervised learning problems are clustering and dimensionality reduction. So let's speak a little bit about clustering. So what are you given? You are given just points X in some space. Like in my on my picture, you have points on the two-dimensional plane, and your goal in clustering is to split the data into the groups of similar objects. So, and on the picture, you see an example of such a clustering where I have split my data into two groups, like blue points and red points. What is important, what is the difference with classification, is that I wasn't given any labels beforehand. I just only look on how my points are positioned in the space and tried to unite in one group the similar objects, so the ones which are close to each other. And the dimension reduction is a very different problem statement, which aims to find low dimensional representation of the data that keeps the properties of the data. What is meant here is that your inputs X might have very high dimension. Like, for example, the shape of aircraft can be determined by hundreds, if not thousands of parameters. However, for the properties you measure, it might be that some parameters are not important, or probably only some combinations of input parameters are important. Like in example, I have a three-dimensional S-shaped figure. However, by problem statement, the properties of the points I have here, they're determined only by relative position of points, not in a three-dimensional space, but on this two-dimensional surface. And thus, having a data set of points which are sampled from the surface, I may target the problem of reducing the dimension. And on the right, I have the result of such a procedure. So instead of three-dimensional data, I get a two-dimensional data, but which preserves the relative positions of points on the surface. That's, of course, just a toy example. And however, multiple real-world examples of such problems exist. And it's generally useful in practice to do dimension reduction to improve efficiency of the procedures you are developing and to get a better quality of the algorithms you are working with. All right, so that were four arguably main problem statements in machine learning. And now we will continue with some deeper look into, first of all, regression and then also classification. All right. So I want to illustrate all what I will be talking about with one particular example. So I will be working with Olympic marathon data. So all of you know that at Summer Olympic Games, there is always a marathon event, which has a huge history coming back to like ancient Greek times. The modern marathon and modern Olympic Games started in 1896, and every Olympic Games have this event as a part of the program. And yeah, I just give a picture of one of relatively recent Olympic champion, Kiprotich. However, let us look what is this data like. And here we start to looking on the code. And as always with machine learning, we start with like importing some libraries. And in my case, I need some very, very basic libraries. And I'm pretty sure that you will be working with all of them. They include NumPy, Pandas, Seaborn, and Matplotlib. And well, NumPy is a library for manipulation with matrices and arrays. Pandas is a rich data processing tool. Seaborn is mostly for some fancy and easy visualization, and Matplotlib is a very powerful plotting library for Python. All right, so let us upload the data. So I'm uploading the data from a file.csv with comma-separated values file, and use Python's. I use Pandas library for that, and I plot just 5 first items of my data set. So basically, in my data set, I have 2 columns. The first one is the year, so when the event took place, like 1896, 1900, and so on. And then I have a pace, which is basically how many minutes the winner of marathon was running 1 kilometer of his trip. You know that the whole length of the marathon distance is a little bit more than 42 kilometers. All right, let us look further how this data looks like. I plot the data, and we see all the data points. So we see that generally we have a decreasing trend. Like we see that the results were improving. There was an outlier in 1904 because the marathon that year was badly organized. Then we have then obviously there were no Olympics during the Second World War. And also we see that after the war, the results somewhat deteriorated for a year because, well, obviously, probably sportsmen were not training that much during the war. But generally, we see quite stable decreasing trend. And what we want to do, we might want to, well, try to approximate this dependency to see how this trend on average looks like. Okay. And if we think, how can we approximate this y variable always based on the x variable? Arguably, the simplest dependence we can consider that can be a straight line, right? It's a very simple function. F of x is mx plus c. And the question which arises, well, I have some such a line plotted on the slide, and the question is how can I construct that? How can I determine these values m and c in order to obtain this linear dependence? Okay, let us look on one possible approach to do that, which is called least squares criterion, or the criterion which optimizes the sum of squares error. So I have a formula on the slide, and let us look on it carefully. So what I want to do, I have my n observations, and I take variable y, which is my output, and subtract from it my function value at this point. So probably we can look immediately on the right part of this formula where I explicitly put here the linear function. So what I do, I subtract from yi, I subtract m times xi minus c. I square this, and the value itself, y minus mx minus c, it's called the residual. So how much I miss at a particular point. So of course, if I approximate my data by a line, there might be some like errors, as we've seen already. So I compute the errors squared, and I sum them over all the data points I have. And what I can do with this criterion, which is called usually sum of squares error function, I can try to minimize it. So what does it mean? I consider it as a function of m and c, and try to find such values m and c which minimize this function. So the ones which are optimal in terms of mean squared error. And then if I have found such values, let me denote them m hat and c hat, then I can do predictions. So I can use these values m hat and c hat, plug in the new value x, and do my predictions. Well, you may ask how to do this minimization. And for linear regression, there exist an explicit formulas which are based on just all the points xi and yi which you have in the trained data. So you get explicit formulas. I'm not providing the formulas in this short tutorial, but you can easily find them in any textbook. And however, in general, when your model is not a linear function, but something else, what you can do so-called numerical optimization. You can try to find values m and c via some steps, improving this value step by step. And the mainstream approach for that is called gradient descent, and the most popular nowadays is so-called stochastic gradient descent. And my colleague Ali will cover that briefly in the second part of ML tutorial today. All right. So what we have just learned is that we can specify sum of squares criterion, and we can optimize it to obtain the optimal values of parameters. Okay. Let us go further. Our example is notably having one-dimensional input. So there exists just one input dimension, and that's why we have just two parameters of our linear function, m and c. However, in practice, we usually work with multi-dimensional dependencies. And in this case, each object x, it's described with multiple numerical features. And in this case, we still can consider a linear function of them. And the general formula for it is written on the slide below. So it's sum of some weights. Now I call this weights wj. And xij here is j's feature of the input object's number y. And still we have an intercept term c, which we also may want to fit. Okay. And let me complicate it one more time, mentioning that in general, we may consider more complicated features, not just the features which are given in your initial data set, but you may try to generate your own features, and you might consider several of them. So usually this process of like creating new features is called feature engineering. And well, it's probably not immediately clear for you what these features could be. There exist multiple variants. And I will give you just single example of such features. So imagine you have a one-dimensional input, x, as in my marathon example. And in this case, I might consider so-called polynomial basis. So my features will be 1x, x squared, and so on, up to some power x in the power m. And then my resulting prediction function will be polynomial. So it will be sum of wj, which are my weights, times x in the power j. So that's going to be some polynomial functions. Well, I'm repeating myself a bit. All right. Still, this model is called usually linear regression. Why? Because this function is linear in weights wj. And algorithms for finding the optimal values of this wj is the same, independent of what features I consider. Okay, let's go back to our marathon data. And let's try different functions to fit this data. So I have two parts of this picture. On the left one, I have my data in red and approximation in blue. And on the right, I will plot my sum of squares error for the training data. Okay? So if I include just a constant value, which means my line will be a constant line, I get error, which is here like more than 0.25. Then for my linear function, so mx plus c, I get this error, which is already less than 0.1. Now, let me go further and see. So what I mean by further, I will increase the power of my polynomial. So I will consider, instead of linear function, I will consider quadratic, cubic, and so on. So now we have a quadratic function. We clearly observe on the left pictures that we have now a better fit of the training data. And we see on the right that the error has improved. So that's great. Let's probably go further. Now I have a third degree polynomial. Well, obviously, we again improved. We see it visually and also we slightly in terms improved numerically. Let's go further. And that's now the polynomial of degree 4. And again, we see the slight improvement and our training error on the training data improved a little bit more. Well, probably we should go one more step, right? We go one more step. And on one hand, on the right, we see that our error improved a little bit more. But on the left, we see that some weird things start to happen. We see this strange trend upwards on the right end of the plot. So you might start thinking that something goes wrong. And actually, if we increase degree of polynomial one more time, so it's now the polynomial of degree 6, we see that something goes probably completely wrong, right? So our functions start to look very weirdly. And however, the training error has improved again. So some of you might know what happened and how it's called. For those who don't, and of course for everyone, I will give an explanation of what is happening just in few slides. Okay, but so far what we have seen how we can do a bit of feature engineering, increasing the degree of our polynomial, and we see how we constructed linear, or well, you can call it polynomial regression, and see how for different degrees of polynomials we have different approximations. All right, let us go further. And just I will mention that, of course, there exist many methods to do regression, not just linear ones. You can do regression with neural networks, with support vector regression, nearest neighbors, Gaussian process, regression trees. There exist numerous different methods. And there is a whole field of study, and you might want to use some of more advanced methods in your work during the Olympiad, but today I'm again mentioning that we're covering basics. Yeah, also I will not go through the code right now, but we will give you access to this Jupyter notebook which I'm showing, and in the notebook I have a full code to reproduce my Olympic data experiment. So you can plot everything, you can construct linear model, you can construct polynomial model, and so on and so forth. So you can reproduce those results, but I won't spend more time on that, and let us go first. So let us now speak about model selection and cross-validation. And we have already observed that when we had a high degree of polynomial, something weird started to happen with our approximation. So the training error was improving. However, just visually, the approximation became worse. So what was going on? Let us look on a different example. So here is my data. So again, one-dimensional input variable and one-dimensional output. These are my points. And I may want to do again a polynomial regression to work with this data, right? So what I will be looking on, a mean squared error on the training data first. And so essentially the sum of squares error divided by the number of points. Okay, so I'm using here the simple scikit-learn toolbox, and so I provide my data x and y, feed the model, and then predict, and then I do the predictions, and I plot the data. So this is a linear model, so the linear regression model. And on top of this picture, what I'm doing, I'm printing the mean squared error for the trained data. So you see that for this linear function, my error becomes a bit more than 32. Okay, well, we already know that we can construct polynomials. Let's do that. Let's add features x squared and x cubic. I'm not going to detail how you technically do that with scikit-learn, but it's pretty natural. So it provides you all the necessary tools to do it efficiently, not manually. And what we see is that our polynomial of degree 3, well, it looks like it fits data better. And we see that the train error has improved. So it was 32, now it's 28. So we have a better fit of the data. Okay, probably we can improve further. And I'm going now a little bit extreme. I'm using the polynomial of degree 9. And I observe very weird picture. First of all, you see here piecewise constant function. And some of you might think of what's going on. We were constructing a polynomial. Here, the answer is very simple. The thing is that I plot my function only at the points of the training data. What's actually happening here is that my polynomial is went through all the points. I will give you a more detailed illustration in a couple of slides. So, well, what is most notable from this plot is that our train error becomes almost 0. You see it's 3 times 10 in the power minus 12. Well, it's like 0, much better than 32 or 28. Let's look more precisely on the way how this data was generated. So actually, my data, these red points on the right, they were generated from a linear function. What was added to this linear function? It was some noise added. So it was a linear dependence, but at each point, it was some random noise, random Gaussian noise was added. And if I generate more points, the blue points on the left, we see that there is no any complicated dependence. That's just a linear dependence with noise around it. Okay. And in this sense, we might think that, well, probably a linear function or low degree polynomial should be good. And in fact, what I can do, I can plot my polynomial of degree 9, now the real plot of the whole function, and you see that it actually behaves very weirdly. It fluctuates a lot, and it looks very strange. So that's a phenomenon which is called overfitting in regression and generally in machine learning. What happened? You have chosen a very complicated model and it fitted your data very well. So you basically fitted the noise which you had in the data instead of the fitting the actual dependence. And if you, for example, as on this slide, you will compute mean squared error, but not on the trained data, but on the test data, then you will see that, for example, third degree polynomial had this error of 27, while the ninth degree polynomial will have the huge error of like 25,000. So once again, we observed small error on training data. We observed very large data on the testing data. That's very common in machine learning. That's very easy to achieve. Why it happens? You chose a model which had many parameters and which was able to fit the data very well. And usually in machine learning, it's very easy to take a model like that. So some neural network might have thousands or millions of parameters and it can fit anything. However, if you very well fit the training data, it doesn't mean at all that you will be predicting well on new data. And that's exactly what we illustrated. We have fitted the trained data very well with this 9th degree polynomial, but we actually failed to fit the test data well because test data was just linear. And that's why very important problem in machine learning is so-called model selection problem. How to choose hyperparameters or generally parameters of the model to achieve the best performance on testing data. How you can do that? Well, the general rule is to never test on the data on which you were training, because your model tends to fit all the possible noise in the training data and your error on the training data will be lower than on the testing data. It's like the rule which almost always holds. And what people usually do, they either split the available data in two parts, one part being trained data and the other one test data. You fit your model solely on trained data, and then you assess its performance on test data. However, the data is usually very limited. That's why you might want to test more reliably. And one very common approach is so-called cross-validation. So what you do with cross-validation, you take your original data set, you usually do a random permutation of the data in the data set, just to be sure that like some initial order of the data doesn't have any result. And then you split your data in several chunks. In my example, I split the data into 5 chunks. And what you do, you use 4 out of 5 chunks for training, so the blue ones, and the 1 chunk, you use it for testing, so the orange one. And then you just use each of them as a testing. Each of these chunks of data use once as a testing one. And that gives you 5 errors, each for each one, and then you average these errors. Why this procedure is beneficial? First of all, you always test on the data on which you didn't train, so you avoid the overfitting. Second, you test on all the data you have at the end, and that gives you more reliable estimate of the error compared to the case when you just split once in the training test. So generally, overfitting, it happens all the time. You should be very careful with it. And one of the ways to assess the model performance in a correct way is to do cross-validation. Okay. Now let us go to the last part of my slides, which is going to be about classification. And I won't have any general discussion for you about, well, how to do classification. I just want to highlight the differences with regression, and then we will discuss one very simple model. So far, for regression, it was assumed that outputs yi, they take real values. In classification, it's different. The values usually take some discrete values. And the simplest example of classification is so-called binary classification, when your labels take just 2 values. For example, it could be 0 and 1. And in regression, you usually predict these numerical values themselves. In classification, usually the approach is a little bit different. You don't predict the values themselves, you predict the probabilities. So the probability that, or the likelihood that your class is this or that value. And for binary classification, that becomes just a probability of a class number 1. So it's a number between 0 and 1, and the higher this number, the more likely the particular object to belong to class 1. And particular model, which I want to give you an idea about, is called logistic regression. So what is logistic regression? Logistic regression is the model which predicts this probability of class 1 in the following way. You have an exponent of a linear sum of the features you have. It looks a little bit like a linear regression. So you have, again, a linear combination, but you have exponent in numerator, and you have 1 plus the same exponent in the denominator. It's sometimes convenient to introduce so-called logit function, which is just a logarithm of probability over 1 minus probability. And this logit function exactly this linear function which we use for modeling. Well, might be not very clear what's happening, but let us now look on this slide. And essentially what we do, we have an input for this, so our probability is modeled as exponent of some variable divided by 1 plus exponent of this variable. And this function naturally takes values between 0 and 1. And instead of x here, we put the linear combination of our input features, and it gives us a probability value for a particular object. Okay, well, some probably interesting way to predict probabilities, how it works in practice. Imagine that you have estimated the parameters w somehow, and then how can we do prediction? We can do prediction in the following way. We say that we predict value 1 if the probability of class 1 is higher than probabilities in class 0. And otherwise, if it's smaller, then if probability of class 0 is higher, then we predict value 0. And it appears that for logistic regression, this rule, which looks a little bit complicated, actually boils down to comparing the value of logits with 0. So basically, you compare this linear function with 0, and that gives us a very simple rule. So for example, I have a two-dimensional example below. I have a line in two-dimensional space, which is determined by like the sum of wj, xj equal to 0. This is this solid line on my plot. And then to one side of it, I have positive values. I predict one class, and on the other side of this line, I predict another class. Okay, so that's how logistic regression works, and why it's called regression, because it just acts similar to linear regression using this linear function. And it might be very confusing for newcomers because logistic regression method is actually doing classification. All right, so similarly to regressions, there of course exist many different methods which also do classification, like k-nearest neighbors, support vector machines, decision trees, random forest, gradient boosting, neural networks, and many of them. So they have different properties. Some of them are much more complex than the logistic regression algorithms that I just described. And I think it's like worth learning them one by one, depending on the needs which are required for the problem you are solving. Well, and here I come to the end of my presentation. I have a little bit of the literature which you might be interested in. So there are several textbooks on different aspects of machine learning and a little bit of statistical inference. They are all undergraduate or even graduate level books. Which means university level books, but all of them are written, I would say, in accessible manner, and you may try to use them as a reference material when you will try to understand how the particular algorithms work out, and how you can, and for which type of the data, which algorithms are better, and so on. So that's, I think, all I plan to cover in my part. So there will be a second part of ML intro, which will be covered by my colleague Ali. And I think that's the right moment to take some questions if any of them are available.
Thank you, Maxim. I'm going to Rossi and Laura for any questions from YouTube. And just a note, after the questions, let's take a 10-minute break before continuing with the next module.
Certainly. So one of the questions, in case of submissions, will the best submission be taken into consideration or the final one?
Well, I can answer that all the detailed rules about the submissions will be posted. So please just stay tuned, don't worry, and we will have the detailed and precise rules available.
Okay, just making sure this one is asked as I need to step out for a moment. Will time and memory complexity be a factor of the judgment?
We did discuss this one, yes.
Okay, sorry about that. So yeah, just one question in the chat. So yeah, let's take a 10-minute break till so 4:35 our Bulgarian time, 10-minute break for everyone.
Yeah.
Okay, thanks
Okay.
everyone for listening, and we will distribute the slides or in the format of Jupyter Notebook to everyone. Thank you.
See you in a Ali, I believe you can speak because the feed is paused anyway on YouTube. If you need to double check anything about the screen or the audio, you can do it now.
Yeah, I have done it.
Okay. back in. The next lecture will be by Professor Ali Sharifi. Ali, please share your screen.
Do you have my screen?
Yes.
Okay, great. So let's start with a very brief introduction to classical machine learning. My name is Ali Sharifi. I'm a faculty member of artificial intelligence and bioinformatics at Sharif University of Technology, and I'm a chair of the Scientific Committee, International Scientific Committee of Informatics Olympiad, IOAI, as well as a member of Scientific Committee of International Olympiad of Artificial Intelligence. So today I'm going to introduce many topics that are covered in classical machine learning. My talk is towards the mentors mainly rather than students. So there are complicated items there that should be somehow translated into software language that is more understood by high school students. So please regret me if you see some formula, some hard items. Just I want to make sure that many items that are covered in classical machine learning are discussed here. So from Maxim's session previously, you understood that there are methods of clustering. And by clustering, we mean that we have a number of samples, but we do not have labels on them. So this is a kind of unsupervised method rather than the classification that we have the same number of samples, but each sample is assigned to a class. So the idea here is that we want to find out the most similar clusters of samples and put each item or sample into one of those clusters. So we have different types of clustering. There is hard clustering that we want to assign each sample exactly to one of the clusters. Rather, we have soft clustering that it's kind of probabilistic, that we compute the probability of each sample to belong to each cluster. For example, here you see a hard clustering. Each sample belongs exactly to one of the clusters. Here you see these samples are most likely to belong to cluster 1. These samples most likely belong to cluster 2, but these samples in the margin or the shared area have the equal clustering ability to belong either to cluster 1 or 2. One of the most widely used clustering algorithms is called k-means, and k is a parameter, the number of clusters that we initially decide. So for this figure, let's say we already know that these samples belong to 3 clusters. So we decide this parameter k equal to 3. And we start by putting 3 random centers on the plane and assign each sample to the closest center. So these samples are assigned to this green center. These samples are assigned to this blue center, and these samples are assigned to this red center. And then we move or relocate this center to the center of mass of each cluster. For example, the center of mass or average of X and Y values of the samples in green color is here, in blue color is here, and in each have many different of sample located. Yeah,
Alex,
is there?
your connection seems to be breaking. We're losing you a little bit. Anything you can try to do about that? Ali, we've lost your audio completely.
Do you have my audio right now?
Yeah, okay. Now
Okay,
it's
good. Okay, good. Sorry. So there are many different clustering algorithms depending on the style or the shape of the input data, the clustering algorithm that the best matches our data might change. So there is a package scikit-learn in Python that you can simply import, and you can choose your clustering algorithm based on among many different options. The next item is support vector machine. So it is the classical machine learning algorithm that was used for many years for classification of the input data. So the idea here is we are given some samples, but each sample has a given class. And we want to find out a simple line or a hyperplane. And a hyperplane is very similar to a simple line, but in n dimensions when n is above 2. So you can think about this plane in 3 dimensions, and you can think about an equation here in higher dimensions that is separating our samples from different classes into different classes. So the idea is what is the plane or hyperplane or simply line here that has the best classification margins. And by classification margin, I mean the boundary between different classes. For example, if we choose this line here, it is very close to the points here and very close to the points here. So for example, if a new point arrives here, then we misclasses this new sample as a red class sample, but this is incorrect. So with this given data, the optimal hyperplane would be this one that has maximum margin from the samples of 2 classes. So there is a mathematical notation for it, and we can choose these values of beta such that the margin is optimized. So there might be different problems. The first one would be noisy data. For example, there is a point here that belongs to this cluster or this red class here, and it makes our best classification line here, while we know this is just a noise and we could draw a line here. The other so to handle this problem, we could add soft margin cluster. So there is a parameter C here that we can balance how much we would allow noisy data and how much we would care about the size of the margin. The other problem is whenever our data is non-linearly separable, means there is no line or there is no hyperplane that divides the different classes. And you can see, for example, these two data sets. The blue points versus the red points are not linearly separable. And here we can do a feature engineering, for example, add new features. For example, if our original features are x1 and x2 means the x and y of the points, we could add somehow, for example, x1 to the power of 2 to the power of 3, or x1 times x2, and this is called feature engineering. So with initial features, we are adding or developing new features such that based on the new set of features, we could find somehow a linearly separable subspace. And this can be enhanced to these kernel functions, and these kernel functions relocate the original samples into a new higher dimensionality space, such that the points were not linearly classifiable here, but they can be linearly separable in the new dimensionality space. So, and the support vector machine can be done in many different ways. For example, whenever we have only two classes and we want to find a binary classification problem, or whenever we have multiple classes and we want to do three classification algorithms, for example, three lines that each line only classifies one class versus the other classes, or we can do it one versus one and find out all combinations of classifiers for each pair of two classes. So to ensure our classification is done greatly, we have different metrics here. For example, whenever you do a classification, a binary classification, for example, given our data is a set of normal or cancer samples, and we have a test. So we already know that there are a group of normal people and another group of cancer patients. And we have a test, and based on the actual state of each person that has negative cancer or positive cancer, and the outcome of our test, which is negative or positive, we can group all samples into four categories. For those true positive samples are those people that have cancer and our test is positive for them. Those true negatives are the healthy people that the outcome of test is negative for them. But we might have false positive cases. For example, those healthy people that the test is positive but wrong, or false negative, those cancer patients that the outcome of the test is negative for them. And we can compute different accuracy metrics. For example, the accuracy is total of these two cells divided to all four cells, which is the number of samples that we correctly identified divided by the number of all samples. And we can compute the sensitivity or recall, which is the number of true positives to true positives plus false negatives. And the sensitivity means how sensitive is our test. Whenever a cancer patient is tested, is our test sensitive enough to make an alarm about a positive cancer patient? And specificity means the number of true negative divided by the true negative plus false positive, or true negative divided by the whole row here. We can also compute a true positive divided by the whole column here, which is called precision. We can compute F1 score. And it's very important that whenever our number of samples are not balanced, actually, for example, 95% of samples are cancer negative, and we have only 5% of people cancer positive. If the test is negative for all of the people, we have 95% accuracy. But it does not mean that our test is something valuable. Our test is simply rubbish because it is assigning every person as negative. So we should, in imbalance cases, we should care other metrics like F1 score or sensitivity and specificity, or sensitivity and precision, and it is called recall versus precision, in order to make sure that the test is working great. So we can assign a threshold, for example, for our test. For example, consider a test of cancer, which have some sort of signal, and we can assign a threshold. Above that signal level, we say the test is positive. And below that signal threshold, the test is negative for patients. And the question is, what is the threshold that best distinguishes between these group of patients? So, for example, here there is an algorithm that assigns a catness score to each sample. So more score means the sample is more likely to be cat, and less score means more likely the sample to be a dog. And the question is, whenever which one of these thresholds we can assign such that the samples above that threshold are assigned as or predicted as cats. So, for example, here we have 100% specificity, but at the cost of reduced sensitivity. Here we have 100% sensitivity at the cost of reduced specificity. So we might decide here that both sensitivity and specificity, or precision and recall, are great. So we can think about this threshold as some trade-off between sensitivity and specificity, or between precision and recall. And whenever we increase precision, we have lower recall, and vice versa. So we can plot these curves. For example, it is called false positive rate and true positive rate plot. So our idea is the random assignment is simply here. And if our classification method works perfectly, we'll have a curve like this. But in many cases, it is not the curve like this. So if we have this curve with higher area under the curve, it would be better than, for example, this orange one with lower area under the curve. So let's introduce other items of classical machine learning. So a very important item on classical machine learning is loss functions. So you already understood that, for example, in regression problems, there is this mean squared error, which means that the difference between the true value of each sample versus the predicted value to the power of 2, and we compute the mean or average value among all samples. So we have also mean absolute error, which simply we replace this power of 2 to absolute function here, but the mean function is the same, or mean absolute percentage error, or other regression losses. And our problem for regression is simply an optimization that we have this input data. We want to find the parameters of the model. For example, whenever our model is a linear model, we have this beta 0 and beta 1, which are the parameters of a simple line. And whenever our model is n-dimensional plane or hyperplane or some sort of, for example, polynomial with a degree greater than 1, we have multiple parameters, and we want to find out a set of parameters that minimize the this loss function. You can see these different loss functions have different effects on the our model. For example, if we want to use the mean squared error with small changes or with small errors, we have lower loss value in comparison when we are using the mean absolute error. But in the larger errors, the loss function for mean squared error is significantly higher than mean absolute error. So depending on the problem, if we want to allow very small errors but disallow very large errors, mean squared error is a better choice for a loss function. But if we want to disallow even small errors, a mean absolute error might be a better option. And we have these loss functions for classification problems. So whenever we are doing a binary classification, we can think about this binary cross entropy function that, again, yi is here the true label of the point. So each sample or point is labeled as 0 and 1 regarding whether it belongs to class 1 or 2. And this value is the predicted value of yi. And so if both yi and pyi are both this pyi is the probability whenever our model is assigning a probability for the sample to belong to class 0 or 1. This is the probability. And if, for example, the sample is belonging to class 1, and this probability of class 1 is 1, so the log of 1 would be 0, so there would be 0 loss here. But if the sample is belonging to class 1, but the probability is computed to 50%, so log and log is done in base 2, so the log of 50% would be -1, and -1 times 1 would be -1, and because this minus here, we will have a loss of 1 here. If the probability is even less than 50%, for example, it is approaching to 0, so the logarithm will approach to the minus infinity, and times this minus will be plus infinity, so the loss function will increase a lot. So we want to minimize this classification error when we are doing binary classification. So this is very symmetric. So this is just the very same phenomenon, but for the samples that belong to class 0. And we could enhance it to multi-label classification, which is called the simple cross entropy. And there are other functions. For example, this cross entropy is very similar to KL divergence, which is used to compute the difference between two probability distribution functions. So let's start with artificial neural networks. We already studied these support vector machine or other very simple machine learning approaches, but we'll face much harder problems, like whenever we want to classify images and say which these images are cats, the other images are dog, or whenever we have a sentence and we want to decide the translation of this sentence from German to English. And these are much complicated problems that these simple classification or clustering algorithms do not work on it very greatly. So these artificial neural networks are the basis of revolutionized AI performance that started mainly they started from many decades ago, but they are at the center of focus since 2012, and because they did great in many very challenging problems like image classification. So the idea comes from biology. So whenever you think about a neuron, there are these dendrites that receive the electrical signals from the neighbor cells, and there is one axon that transmits signals to the other cells. And there is a cell body here that is either in firing state or not firing state. You can think about it a neuron as on or off, or as 1 or 0 state. And we can turn the same neuron into this very simple mathematical formulation that you have these inputs. Each input can be simply a number, and we multiply each number to a weight. These weights are parameters to be learned during our machine learning algorithm. So you can think about these inputs as different pixels of an image or different words of a sentence or anything similar to that. And these weights are initially assigned randomly, but during the machine learning, I will tell you how these weights are updated in order to make the correct output at the end. So each parameter xi is multiplied by this weight, and they are summed together, and a bias, which is very similar to the intercept whenever we have a line equation here. So this bias is also a parameter. It could be assigned randomly initially, but during the machine learning process, this bias is also updated. So these values are all summed together, and it undergoes an activation function, which makes the output not linear. So you remember from support vector machine that linearly separable problems are very simplistic, and many problems do exist that they are not linearly separable. So this activation function provides nonlinear activity to our neural network. So there are many different types of activation function. You can see here one very simple choice would be rectified linear unit, which is simply the same value of x whenever x is greater than 0, or 0 whenever x is less than 0. And there could be ELU, leaky ReLU, or tangent hyperbolic, or sigmoid. And this sigmoid function, for example, is the most one of the best choices whenever we want to do a classification. For example, if the value of x is towards minus infinity, so the output value would be 0, and whenever the value is towards plus positive infinity, the output value is 1. So this is very similar to off and on state of a neuron, but this shape makes a nonlinear separation. And we have many different activation functions. If you import Torch in Python, you will see many different activation functions do already exist in PyTorch library, so no need that you develop this activation function by hand. So this is very important. This softmax is a kind of activation function for the last layer whenever our problem is classification. So the softmax is one of the most important and widely used activation functions for a multi-class classification. So I talked about updating the weights and how it is done. It is done by a gradient descent algorithm. So we have the loss function here, and we want to find out weights in such a way that they are optimized in minimizing the loss function, and that's the whole idea. And whenever you are located here, you can think about you are standing on a mountain and your goal is to reach the deepest part of the mountain. So if you are looking at the whole landscape, it's very simple to find out the deepest area, but this is not the case whenever we are trying with many kind of different optimization problems that you are staying here, and based on small changes to your weights, you can decide, okay, if I increase this weight, my loss function is increased, but if I decrease this weight, my loss function is slightly decreased. So the best idea here is to decrease the weight. But if we are standing here, by increasing the weight, we will have a lower value of loss function. So the idea is similar to this. So from each position or from each set of initial values of parameters, and by parameters I mean all weights and bias values, we want to find out the gradient there. And the next step is to update these weights, all of the weights. By weight, from here to the end of the presentation, I mean both all parameters, meaning all weights and bias values. So the weight of times plus 1 is the weights of the previous time minus some parameter which is called the learning rate times the gradient of the loss function. And the gradient means a vector that is towards the most increased way of increasing the loss function. So minus is exactly in the reverse position, that is decreasing the loss function. So whenever we have a single layer perceptron, and a single layer perceptron means we have these inputs and we have only one layer of neurons that are deciding the outputs based on these inputs, we can do very simple problems. For example, it's very hard or impossible to do many of these classification whenever we do not have a line that perfectly classifies all of the points of two classes. So to solve this, we increase the number of layers. For example, this is called multi-layer neural network or simply deep neural network. By deep, we mean there are many layers in our neural network. So we start with this input layer. We have a number of hidden layers, and we have one output layer. And the output layer might have one neuron whenever we have a very basic binary classification, or we might have many neurons here in the output layer. And the question is how many hidden layers we might have, or how many neurons in each hidden layer we might have in order to have the best results. The answer is not simple, so it really depends on the problem. It depends on the data, and it depends on many other factors that you might have. So the best way is to look at different best practices, top state-of-the-art models, in order to have an idea what is the architecture of best performing neural networks in this specific problem. And by trying and doing exercises on many different problems, you will have an idea whenever to increase the number of layers, whenever to increase the number of neurons per layer, when in which layers you should choose which type of activation function. And there are many different things that you can play with. It's kind of Lego that you can build many different types or many different architectures of deep neural networks, and some of which work greatly on each problem. So the idea of these deep neural networks while training, and you remember from previous session by Maxime that we have a training data and we have a test data. And by training data, I mean a subset, for example, 70% of all of the samples that I do have that I use in order to decide the best performing parameters and hyperparameters. By hyperparameters, I mean the number of layers, the number of neurons per each layer, the type of activation functions. By parameters, I mean the weights and the bias values. So based on the training data, we provide, we update the values of parameters. We can split our data into train, validation, and test data. For the test data, we do not touch the test data until we have fixed the number of hyperparameters, and we have find out the optimal values of parameters. And finally, we go to the test data. But what is the difference between the training and validation data? So we for example, choose 60% of the data for training, 10% for validation, and the remaining 30% for test. So based on 60%, we choose some architecture. Based on this 60%, we update the weights. Based on the rest of 10%, which is called validation data, we evaluate the performance. We might here decide to change hyperparameters, for example, decide to increase the number of neurons or decrease, or increase the number of layers or decrease, or change the activation functions, and do again the whole training procedure on this new architecture of a neural network, and then use the validation data in order to evaluate the new architecture. And we repeat this scenario of training based on the training data and evaluation based on the validation data in order to find out the architecture that is best performing, along with the parameters on that architecture which are best performing. And whenever we are in the final stage of, okay, this architecture is the best, these parameters are already decided, we go once to the test data and evaluate the network on the data that is not seen already by the network. If we go to the test data and alter the parameters or hyperparameters based on test data, we are actually cheating, because our network is already has the results of the test. So the values, the metrics are not reliable anymore. So during this forward propagation, we put the one of the training data here, and we evaluate the number, the value, the output value of each neuron layer by layer, and go on until we compute the outputs. And the predicted output might be similar to the actual output, or might have error here. And the idea is to backpropagate the error in order to update the parameters here. And this is the backpropagation. So in another backward propagation, we compute the gradients, and the gradients means the derivative of loss function with based on each single parameter in the all layers of the network. And how it is done? So how? Yeah.
I'm sorry to interrupt, but we have to end this session pretty soon. If you think you can wrap it up in another minute or two, let's do that. If
I'll try my best to be very rapid. So there are many many very simple ideas. So in the forward pass, we can simply use this chain rule here. So if we already have the derivative of loss based on this output, we can calculate the derivative of loss with respect to x and y by multiplying this del L to del Z times del F to del X, and the F is the activation function here. So it will gives us del L to del X. And the same can be done for del L to del Y is simply del L to del Z times del F to del Y. And we, based on this activation function, we already know the del F to del Y. And we can, in a forward pass, for example, 3 to the power of 2 is 9, and 9 multiplied by 4 is 36, and 36 divided by 2 is 18. And the del F to del F is simply 1, but we can backpropagate the values based on this chain rule here to compute all of these values, and based on the very simple gradient descent that I told, we can update the parameters here. So there are many ways of doing it. For example, we can choose a we can give the whole batch of the training data in each iteration. We can randomly select one sample, or we can split the whole batch of data into mini batches and to do it, which provides the best idea, the best results. So we can do it into many different batches in iteration, and we can do the same thing again with our training data, which is called epoch. Until 100 epochs, our network might be very well. So I skip the details here, and there are many parameters that we can play with. For example, the learning rate. We can think about overfitting, and we can introduce regularizations or do early stopping, and we can think about many different approaches in order to achieve the best results. And if you want to have the complete slides here, it's simply you can go to my GitHub and from the slides section, you can have all of these slides along with many other slides. Thank you very much.
Thank you, Ali. We will also share the slides in a link after the via email after the session. So in the interest of time, I will skip the question session now. We can take questions after the NLP lecture. One comment on YouTube that I can see is, are these lectures for high school students or for university students? Understandably, it's difficult to adapt this kind of material for high school students, and the hope is that the team leaders will take the most essential from today's lectures and translate it as much as possible for the high school students that they're training. Hopefully with the NLP lecture, things will be a little bit more low level. Let's see. Okay, I think everything should be fine now with the slides. So, okay, slideshow. All right, we're talking now about the basics of natural language processing. We all know ChatGPT, we have all interacted with it. You know that if you go and ask it what is 2 + 5, it will tell you the correct answer. Since ChatGPT is a proprietary model, we don't really know exactly how it works, but we have good reason to believe that, and actually in a technical report that they did reveal certain details about the model, we know that at the very core of this model lies a language model. At the very core of this AI agent lies a language model. And what a language model is basically something that, you know, on the forefront, we see this dialogue-like user interface. But what's happening in the back is that there is this model that basically gets an input that might be formatted something like user says, what is 2 + 5, agent, and then from this input, the model has to generate the next token. Or rather, it has to generate the full string that we see as an answer. But effectively, what it's doing is it's generating one word at a time. So given our question, it might start by generating the word 2, and then generate plus, and then generate 5, and then generate equals, and finally, the key answer here, the word 7. So language modeling is all about predicting the next word in a sequence of words. Formally, what we're looking for when we want the language model to predict the word 7 is a probability for the word 7 out of a list of all the possible words the language model can predict, conditioned on this past context, which is the conversation that has happened so far. And if we assign this probability to P of 7, then we basically want a language model that for this specific context will give us P of 7 that is higher compared to the probability it would assign to the word 8, that is higher than the probability it would assign to the word 20, that is much higher than the probability that it would assign to the word egg, that is completely irrelevant in this context. So let's dive a little bit deeper into what's actually happening here. So on the one hand, we have the input, which is the past text, the dialogue that has happened so far. And we have the output, in this case, the word 7. And in between these two, we have a language model, which basically maps from input to output. That model between input and output is a complex function, usually based on a neural network, which is basically a series of computations which map an input into an output. But because these have to be and just to translate things into some of the terms that you've heard already, and to be sure that there's a clear understanding of what I mean by model and weights. If we take as an example a very simple task we have to solve, where we find that the weight and gender are determining factors in what is the optimal dose of a medication for a given disease, we might find that the model is such that the dose for men should be half their weight plus 80, the dose for women should be half their weight plus 50. So how we might formalize that is to represent the input features as the age of the person, and then a one-hot representation of the gender. What I mean by one-hot is we have these two genders, male and female. These genders are categorical variables, they're non-numeric, but we want to perform some computations with them. In machine learning, we're always performing computations, so we have to have some numeric way to represent them. If we just translate them into arbitrary numbers, that's not going to be very useful for the purposes of computations, because these numbers will not really be meaningfully representing the values of the variables. So we might opt for representing them as what is known as a one-hot vector, where we basically take all of the categorical variables that we have, in this case 2. So, and we create this vector of zeros mostly, of the size of the number of categorical variables, in this case 2, and we assign a 1 for the relevant value of the categorical variable. So this is just to say that we might represent male as 1, 0 and female as 0, 1. And then that allows us to build a weight matrix, which we can directly take the dot product of with the input vector and get the correct output. And this weight matrix is just a visual representation here of what Dr. Maxim introduced as the weights W here, for 1 for each value in our input feature vectors. So having established that, let's see what that looks like for language modeling. So the problem with language, the difficulty, is that words are discrete units. Again, similarly to how male-female is a categorical variable with no natural numeric representation, words are categorical variables that we have to find a way to translate into numbers before we can feed them into any kind of machine learning model. So again, if we were to go about that in the most naive way possible, we might say, okay, we're going to assign the word user value 1, the word what value 2, the word is value 3, and so on. The problem with that is that these numbers are not meaningful in any way. And so any computations that we try to perform over them will be extra hard, because we have to account for the fact that these words are represented by arbitrary numbers. So what we might do instead, similarly to before, is use a one-hot vector. So let's say in this example that our whole vocabulary, all the words that we want to build a model for are the ones present here. There's I believe 12 unique words. So we have a vector of 12 slots. A vector is just an array of numbers. So we're building this vector of dimensionality 12, and we're saying when we want to represent user, we're going to put a 1 in the very first position in this vector, and all the rest will be zeros. When we want to represent what, we're going to put a 1 in the second position in this vector, all the rest will be zeros, and so on. So this now allows us to represent words in a slightly less confusing way from the perspective of the model, but still in an arbitrary way. Still, we have these very many zeros in the vector that don't really serve us any purpose. We have this fairly long vector to represent just a small set of words, and still the representations are arbitrary. So what we can do instead is to use, instead of sparse meaningless vectors, to use dense meaningful ones. And how we're going to go about building these dense meaningful vectors is by following the observation made by Firth in 1957 that you shall know a word by the company that it keeps. What that means is, if we look at the text we have here and generally think about what we know about language, the word equals would often appear in the same sentence as the word plus and vice versa, because these are both mathematical terms. The word plus would also often appear between two numbers. Words for numbers would often co-occur together because we might want to express something like the year 1993, or we might want to say 2.7, and so on. So numbers often co-occur together. And then we can also say the word what is often followed by the word is, because this is often how a question is formed. So all of these observations are things we know as language users, but we don't actually have to manually describe them. What we can do instead is we can build dense vectors based on counts. So we can say, given a very, very small corpus, we would call it, which is just a collection of text, we can take every word from this corpus and put it in a matrix like this of n by n words that are all the words found in our corpus, and then we can just count. Whenever I see the word 3, would I see another occurrence of the word 3? In our corpus here, we don't see that, so we put a 0. Same for glass, but then we go to doctor. In this sentence here, we see the word 3 right here and the word doctor here, so we will put a 1. Similarly for plus, we see 3 plus 8 equals 11, so we would say, I've seen an occurrence of the word 3 in the context of the word plus. We can do that again for the word the, and so on, and then for the rest of the words in our corpus, and we obtain this matrix, which now we can interpret as each row of it. So the horizontal set of cells associated with the word 3, for example, can now be interpreted as a vector representation of the word 3, which is dense in the sense that few cells will be zeros, and it is meaningful in the sense that the vector that we build in this way for the word 3 will likely be somewhat similar to the vector that we build for the word 7, that we build for the word 11, because you can imagine a lot of contexts in which these words will occur in similar positions surrounded by similar words. So for example, all of them might have a high value for co-occurrences with the word plus, because all of them are likely to often co-occur with the word plus. Of course, this has to be derived from a much, much larger corpus of text. And as we will discuss later, in practice, we do learn representations from huge amounts of text, because that is when they are most accurate. Now, one problem remaining here is that these vectors are still going to be the full size, the full dimension, their dimensionality is going to be based on the full size of the vocabulary that we extract from the corpus. Again, by vocabulary, I just mean the number of unique words that we encounter in a large volume of text. So if you think about the English language, different claims have been made about how many words actually exist in it, but let's say it's 1 million. This means that if we take a big enough corpus of English, we extract the vocabulary from it, and we learn vectors in this way, we will be learning vectors of dimensionality 1 million. And if you think back to what was discussed before about how we build neural networks, how we build machine learning models in general, for every feature in our input representation, we have to have some sort of a weight that's going to allow us to determine how much that feature contributes to the final output, which means that for a vector with 1 million features, we will need to be learning 1 million weights. And then it gets very, very computationally heavy as soon as we start learning these weights with gradient descent. But even just storing these vectors, like imagine having to store 1 million vectors of size 1 million on your computer. That's a lot of gigabytes. So we don't want to do that. We don't want to learn these huge representations and models. What we might do instead is, once we have computed these count-based vectors, we could use a dimensionality reduction technique. I know we haven't gone into depth about what that is, but I'm just telling you these exist. You can, in theory, compress this vector into a lower dimensionality which will be more manageable. And people have, maybe 10 years ago, tried to do that, found that at the time it worked all right, but actually what we've learned since then is that there's many better ways to go about learning the representations of words. So I will now talk about word2vec, in case you've heard about that. This is a way to initialize dense low-dimensional vector representation of words randomly and learn them algorithmically through gradient descent. So this is what our embedding matrix would look like. The size of it is V by D, where V is the size of the vocabulary that we've extracted from our text corpus, and D is just a dimensionality that we choose as appropriate for our word vectors. So this could be 100, it could be 300, it could be 1,000, depending on how much data we have to learn from, how much compute we have available, how complex the task is that we want to solve, and so on. In the peak of word2vec, the typical dimensionality of this was 300. The way we go about learning this, or one of the ways that I will cover today, is continuous bag of words algorithm. The training objective here is, given the vectors of surrounding words, we want to predict the target word. So what this looks like, if you look at the training samples down here, is given the words +8 = 11, we would want our model to predict that the word 3 is a likely word to appear in this context. And in this specific algorithm, the context is actually treated as a bag of words, which is to say that the order doesn't matter, which is why I'm representing the context as a set here, just to say that the word can appear anywhere in this context, and this is what the algorithm is trying to learn. As you can imagine, this is not optimal, and we will see in a little while how it can be improved. But in 2012, 2013, this proved to be an extremely effective way for representing words for the purposes of natural language processing. So how we would go about computing the mapping from input to output is we would take the vectors for the context words from our embedding matrix. In this case, the example is 3 + 8, 11, that gets mapped into equals. So we will take the vector of 3 + 8 and 11, and we will actually simply sum them. And what that the implications of that is, again, that the word order doesn't matter, because summation is a function that loses that information. So we just have now this one vector of size 1 by D, which represents the whole context. And we will then take the dot product of this vector with what is called an unembedding matrix, which is has the same dimensionality as the embedding matrix, but it's transposed. And by taking the dot product of these two things, the vector and the matrix, we get finally one vector, which has size V and represents the predicted distribution over the vocabulary. So the first cell in this vector might represent the probability of the word 3 occurring in the context that we've provided. The second would represent the probability of the word glass. The third would represent the probability of the word doctor. And finally, the probability of the word equals would be represented by this cell here that I have intentionally made darker than the rest, with the goal of, with the idea of the intensity of the color representing the probability mass assigned to that token. So since here we want the model to predict equals, we would hope that this specific cell in the vector has the highest value. Because finally, how we would make a prediction is by taking the token with the highest probability from this whole vector. And how we would train the model is we would take this vector, the one to the left here is the output of the computations shown on the previous slide. And the one on the right is the target distribution. This one is just a one-hot vector, which has zeros in every other cell except for the one that represents the word that we want, the target word, the one that we want to be predicted. And by computing the cross entropy between these two, we obtain a loss that we can use to then compute the gradients with which we have to update the embedding and unembedding matrices. The product of this operation is that we have these word embeddings, which are low dimensional, dense, and meaningful, and represent the distribution of words in context. If we imagine a very simplified case where we only train word embeddings with dimensionality 2, which means that we can plot them in a 2-dimensional space, we might hope to obtain word embeddings that look something like this, where the words for bus and car are very close to each other because of how highly related these two concepts are semantically. Bicycle is somewhere nearby because it is still a vehicle, but a little bit different. It's not motorized. Then over here, we might have some furniture. And in between the two sets, we might have the word seat, which sort of has something to do with bicycle, car, but also with chair. So this is the goal in the end, is to have an embedding space in which words are represented in a meaningful way with respect to one another. And this is learned from the contexts in which they occur. Words that occur in more similar contexts will end up having more similar representations, and words that occur in very different contexts will end up being quite far apart in this, well, low dimensional from the perspective of what we talked about before, but still high dimensional from the perspective of, here we only have 2 dimensions. Usually we're working with upwards of 300. Once we have these word embeddings, there's a lot of things we can do with them. One thing is we can solve sequence classification tasks. So Dr. Maxine covered those a little bit. Now I will go in a bit more detail. In sequence classification, the input is a piece of text and the output is a label that classifies the text according to our needs. So one example is sentiment analysis, where we might have some comments users left on a web page, for example, and we might want to classify them automatically into negative, positive, or neutral. The way we would go about that is we would want to have a representation of the input text and this matrix W, which has the dimensionality of the input text representation on one hand, and on the other, the dimensionality of the classes that we're working with. So here W would be a 3x3 matrix because our input is in the dimension, has D dimensions, and there are 3 possible labels we want to predict: negative, positive, or neutral. And by taking the dot product of these two objects, we'll again obtain a vector of dimensionality 3, where each cell, each of the 3 cells represents the probability of class negative, positive, or neutral. That's just the classic linear classifier. And how we will actually obtain the representation of text can be very simplistic. Again, we can assume word order is irrelevant. For sentiment analysis, it often actually is, because as long as we're representing that the text contains the words this, movie, and sucks, this final representation here that can be just the sum of these 3 vectors is going to contain the negative sentiment of the input text. So hopefully the matrix W will accurately reflect that by resulting in a high probability for the negative class. Another task that we can solve, and that is very common in natural language processing, is sequence labeling. Once we can represent words in text, we can perform sequence labeling where the input is a sequence of words and the output is a sequence of labels, one for every word. A very classical sequence labeling task is part of speech tagging, where we have input text like "I like the music," and the corresponding label sequence would be pronoun, verb, determiner, noun, which are the parts of speech of the 4 words in the input. Again, the way we go about this is we have a weight matrix that we want to learn, W, which has dimensionality D by N. N is the number of parts of speech that we might want to predict. And we will be taking the dot product of our input representation with this matrix. In a somewhat naive approach to the task, we can treat each word as a separate input and actually say, okay, first I'm going to classify the word like. So I'll take the embedding of this word, I will multiply this embedding with the weights matrix, and I will get a prediction for the word like. Then I'm going to take the embedding of the word movie, and I will repeat these steps to get a label for the word movie, and so on. The problem with this, however, is that, as you might already be thinking, some words actually have different parts of speech depending on the context, such as the example here, where I like the music is a sentence where like serves as a verb, but in the sentence, it looks like a toy, like actually serves as a preposition. If we take this naive approach of classifying every word separately by disregarding the context, we will always be making a mistake on at least one of these two, right? We will either, our weight matrix will either predict verb or preposition for every occurrence of the word like in our data. So how do we go about solving this? Well, in come contextualized word embeddings. If you have heard about BERT or masked language modeling, this is what I'm talking about here. So these are word embeddings quite similar to what we were looking at before, but now order matters. Because of course, in language, order is very important, and we lose a lot by disregarding it. So having the same training corpus as before, what we're now doing is we're taking training samples, we're creating training samples by masking some part of the text, feeding the masked text as input to the model, and trying to predict what has been masked. So previously, we would have taken +8 = 11 as an unordered set of context words and tried to predict 3, whereas now we're taking it as a ordered string, and we are masking the word 3 and trying to predict it. We cannot do this just with an embedding matrix. We actually need a second set of parameters, which will update the word embeddings with information about the surrounding context. So the word embeddings that we talked about before, the basic ones, they're trained to learn about the general context of words. They're trained to tell us what company words tend to keep, but that is based on an entire corpus. Now we're taking these and we're actually further contextualizing them with the specific context in which they occur in the instance that we are looking at. And the way we go about that is we use an additional set of parameters called an encoder, which is a system of many W matrices, you can think of it just this way, that each take an input and produce an output. And in the simplest case, both input and output have D dimensions. We can just stick to that for now. So how this actually goes is for an input like 3 + 8 mask 11, where we want to predict the mask token equals, we will be passing to the encoder the word embeddings of 3 + 8 and 11, and also a special word embedding for the token mask. And this encoder will contextualize these embeddings with respect to one another. And actually next week, you will learn what is the most common architecture used these days for that and how that works exactly. For now, I will just leave that as a black box and talk about the output of this encoder, which is a set of contextualized word embeddings. So each of these now represents the original word with its semantics derived from the full text corpus, but also with contextualization with respect to the exact sentence in which we're observing it here. So the first contextualized word embedding here would be for the word 3 in the context of +8 mask 11. And the way this model is actually trained is by taking now the representation of the mask token, the contextualized mask embedding, multiplying it again with an unembedding matrix to obtain a probability distribution over the vocabulary, and similarly to before, comparing this probability distribution to the target distribution, which is a one-hot vector where all other words are zero, all values for other words are zeros, and the value for the word equals is 1, taking the cross entropy between these two to obtain a loss signal, and using stochastic gradient descent to backpropagate this loss through all parameters in the model, most importantly, through the encoder and the embedding matrix. So coming back to sequence classification again, let's see how we can do that better with contextualized word embeddings. If we take again the example, this movie sucks, and the desired label is negative, we can now again take the sum of the word embeddings for each word in the input, but by doing that, we're not actually losing information about the word order, because each word embedding is now contextualized with respect to the full sentence, so it carries information about the word order. And there are actually much more elaborate ways in which this can be done, but I just wanted to keep it simple for now and tell you that this is a perfectly reasonable thing to do if you want to perform sequence classification. And coming back to sequence labeling, where we had this problem with the word like, we're now not going to run into this problem, even if we stick to the simple approach of classifying each word independently, because the representation of like here on the left side is not going to be the same as the representation of like on the right side. They will be similar because the underlying word embeddings that we're passing to the encoder carry information about, carry conflated information about the occurrence of these words in the full text corpus, but they will be different because one is observed in the context of I like the music, and the other one is observed in the context of it looks like a toy, and this information is now embedded inside of the contextualized representation of the word. And we've made our way back to language modeling, which is where we started. So how do we go about predicting the word 11 from 3 plus 8 equals? Well, we can conceptualize this similarly to how contextualized word embeddings are trained. You can almost imagine that we solve the same objective as in contextualized word embedding training, but we always put the mask token at the end of the sequence. So we can have 3 plus 8 equals mask. The mask occurs in the position of the next token, which is what we want to predict. And we can just do the same as before to obtain a probability over the vocabulary and to get a maximum over that, giving us the word 11. In practice, we find that we don't even need this mask token. We can directly take the representation of the last token of the sequence, in this case equals, and we can take the dot product of that with the unembedding matrix. So remember that in both of these cases, this last arrow here is a simplification for, where do we have that step? Yes, for this step here, where we multiply a vector with an unembedding matrix to get that vocabulary distribution. But we don't, like I said, we don't need the mask. We can directly do that from the last token in the sequence and train a model again with cross entropy, where this vector has to be as similar as possible to the one hot vector representing the target. And we find that this system is flexible enough to learn good representations of the input that allow it to correctly predict the next token. And the way we would go about predicting yet the next token is by feeding back in what the model predicted on the previous step. So we started off with 3 plus 8 equals. We predicted 11 here. And now we're feeding 11 back into the language model, getting a representation for this now new last sequence token. And we're using that one to predict the next new token, which is a full stop, which will then in turn feed back into the model if we want to continue predicting tokens. So this is everything that I wanted to cover today. Just a couple of last notes about some practicalities around the vocabulary, some things that, simplifications I didn't mention so far, but are worth being aware of. So we usually learn word embeddings and language models from huge volumes of text. As I mentioned, these can go up to 2 billion or sometimes even trillions of words, which means that the unique number of words in this corpora is going to be huge. So even if we're in this lower dimensionality, before I was talking about account-based embedding matrix, account-based word vector matrix of 1 million by 1 million, we have now reduced the dimensionality to an arbitrary value d that we can set to, like I said, 300, for example. But still, if our vocabulary has 1 million words in it, we will be storing and learning this huge matrix of 1 million by 300. It's too much, it's not practical. So we have to make certain adjustment. One common thing that is widely done for language model training these days, or any kind of natural language processing, is instead of using whole words, we split words up into subword tokens or subword units. And this ends up reducing the size of our vocabulary because there are often shared subword tokens between different words. So, this is a completely random split I've made here, but you can imagine that this THR here, from tree could be reused when we're looking at the word throne, could be reused when we're processing the word triathlon, I guess, and so on. Similarly, for each of these tokens, there's, we are basically compressing. This is actually called byte pair encoding. It's a compression algorithm that reduces the vocabulary that we have to work with. And now each of these subword units is represented by a vector. And it's a little bit harder at first to see why these vectors should still be meaningful when they're representing somewhat arbitrary subword units. But where the power comes from is actually that encoder that is going to take the seemingly meaningless units, take the vectors that we've learned for them, and compose them into meaningful representations for the words underneath. I'm busy. So the next thing I want to mention is that still, even with this technique, we might end up learning quite a large vocabulary. And what we would want to do in that case is to disregard very infrequent tokens. We might set a threshold of a minimum of 5 occurrences, for example, for a token to end up in our vocabulary. We would also often introduce an UNC token, standing for unknown token, to cover any tokens in the input that is not in the vocabulary. So even learning a vocabulary from such a huge amount of text, there might always appear a new word that we want to be able to process. And in that case, we might just represent it with this special UNC token and the corresponding embedding that we've learned for it in order to be able to, in some form, pass it as input to our model. And lastly, we introduced a beginning of sequence token to allow models to predict text from an empty sequence. So if we want to just start predicting from scratch, from nothing, we can use this beginning to sequence token as the first input to the model from which it will start predicting the next tokens. And we also introduced an end of sequence token to allow models to learn when to stop predicting tokens. Because if you think about it, ChatGPT somehow knows when it's done generating text, when it's done predicting new tokens, and it has completed the answer to your question. Okay, so with respect to NLP, today we covered word embeddings, sequence classification, sequence labeling, encoders, contextualized word embeddings, and language modeling. Next week, you will learn about transformers, which is the architecture behind the encoder and the language model. You'll learn about encoder decoders and about parameter efficient training. And if you feel that there's anything I discussed today that you would like to get a better overview of, please comment on YouTube. We can try to include it in next week's lecture as well, if time permits. Thank you very much for the attention. Laura Rossi, should we take some questions? Technically, we are now at the end of this session, but if you're able to stick around for a couple more minutes, I'm happy to answer questions.
The last question so far regarded the schedule, and I think you just covered it. You just answered that next week there will be new things, so please join us next week.
Yes. So next week we will have one lecture on NLP and 2 lectures on computer vision, as well as a lecture on coding for NLP, where we will talk about general advice for coding, debugging, common frameworks for deep learning, and others. Okay, while we wait for any questions, I just want to leave with one closing remark, which is this Olympiad is a new event. It's a very timely event with how much AI has grown in popularity and the need for even the youngest among us to be aware of how it works, where it fails, what the role of AI is going to be in our future. But this is the first year that we're doing it. We're putting a lot of effort and passion into designing the problems, in organizing the on-site event and everything. If you have suggestions for, things that you think would work well, please share them with us constructively. And if you find that, we make a mistake here and there, also forgive us, because it's the first time that we're doing this. I'm sure that for next year, a lot of things will be more polished, but we still believe that we will have a great event in Bulgaria in August. We look forward to seeing you all there. I will not be here next week for the webinar, but other colleagues will be giving lectures, again, on NLP, CV, and coding for ML. I don't see any other questions on YouTube, so I guess we can wrap it up.